To build on what Kevin Flood just presented for you all, I'm going to show an example of an integrated mission with a lot of the models that are used to populate these missions. So the mission that we're going to be considering today is looking at a system of systems that needs to be coordinated in order to achieve its objective. So the objective of this mission today is going to be to detect and communicate the location of wildfires across Northern America. So the solution that our team is currently proposing uses multiple Cubesat constellations in coordination to actually do this job. So one of those constellations will be an inexpensive set of CubeSats focusing specifically on the detection side of the mission. And then there's going to be a second constellation for communications relay that's being designed as a shared resource for many other missions as well. So when it comes to evaluating the performance of the system of systems like this, our design reference architecture is going to be composed of a lot of different scenarios that will focus on the various measures of mission effectiveness. Some of those are going to be very specific to the individual payloads or components, while others will be related to the coordinated system's performance as a whole. So the scenario that we've chosen for today is more of the latter, the end-to-end coordinated collection mission. So let's go ahead and take a look at these systems in a little bit more detail. All right, on the fire detection side of the mission, today we're going to be focusing on the sensor performance characteristics. So since our mission is to detect wildfires, we've obtained a data set from the National Interagency Fire Center of all of the current wildfires across North America. You can see that represented in their webpage here in the top left corner. So I've downloaded that data set in a GIS shapefile format. So that describes to me where all of the current wildfires are, and I'm going to use that to define the sample set for the mission today, such that if I do a good job of designing the mission, I should be able to detect all of the fires in this data set. When it comes to the sensor payload characteristics, we need to detect the fires, so we want to capture the image resolution of that sensor. So for today's metric, we're going to be talking about ground sample distance, which is a quality metric determining the size of each fire that we're capable of detecting. If you're not familiar with ground sample distance, effectively it just represents the width of the ground covered by each pixel in the camera. However, to identify a fire, we also need to cross a threshold of the required number of pixels to achieve detection. So for this class of sensor that we're talking about, that threshold is somewhere around 10 pixels. Now, if you look at the image that's on the right-hand side, that's a 3x3 matrix that's composed of 9 different images at varying focal length and varying detector pitch. So the focal length is a sensor property that effectively represents what's going on with the optics, and then the detector pitch is describing the actual collector plate and the size of the pixels on the camera itself. So in general, what you see here from the image is that smaller detector pitch and larger focal length will result in a better ground sample distance. But of course, because of budget constraints and then the mass constraints on the CubeSat, we're making a couple of concessions about the design of that constellation. So first and foremost, the sensing satellites are not going to have a requirement for any onboard storage, which means that any imagery that they're collecting needs to be relayed back to a ground control station in real time. And then also for that communication link, instead of being able to communicate directly to the ground, as mentioned in the previous slide, we'll be making use of a communications relay constellation. So the satellite that's collecting the imagery will always need to have a constant communication link to that relay constellation. So speaking of the communication relay constellation, we're designing this system to support a variety of different missions. So in the case of the design today, we're receiving a lot of information about the relay constellation, but I don't have a whole lot of options to design that or make changes to it. But as mentioned, our imaging satellites won't have the ability to store data, so they need an active link not only to one of those communication satellites, but that communication satellite also needs to have an active link to one of the ground control stations simultaneously in order to complete that whole chain. So the communications constellation team that we're working with has provided us their current system parameters, as well as some of the models that they're using to evaluate how those systems are functioning. So one of the models that they've provided to us is the antenna gain pattern. So the antenna gain describes the relative antenna strength in all directions, either for transmit strength or for receiver sensitivity. So the gain pattern is influenced by a lot of different factors, mostly the design of the antenna itself, but also where that antenna is mounted on the satellite. And then, of course, you also have to take into account the environment that the satellite is operating in. And in this case, we've been provided with a thermal model that actually leads to additional noise characteristics on the satellite receiver end. So depending on how warm that satellite gets, there will be additional noise on that link. So they've provided us the models for that antenna gain pattern, as well as the models and tools to evaluate the thermal environment that it's operating in, and then how all those things work together. So from here, we've described a little bit about what that system is intended to do. So let's extract some requirements from what we've described so far. So first and foremost, the sensing system shall collect imagery with a ground sample distance less than 10 meters. So the reason we're looking at 10 meters is because when you look at that ground sample distance combined with the number of pixels to cross the threshold of detection, in order to detect a 2-acre wildfire, that requires a 10-meter ground sample distance. On the communications side, we've determined that we have enough satellites and we have enough coverage that we can withstand up to about 1 orbital period per day of communications outage and still able to meet those overall objectives of responding. So what we've specified as the requirement here is that the communication system shall provide link availability with less than 7.5% outage. And again, that corresponds roughly to the 1 orbital period per day. The other part of it is the overall system behavior, where we actually need to be able to see these regions and revisit these regions multiple times a day to give the firefighting authorities an opportunity to respond in time. So the overall system shall have a revisit time less than 4 hours to support that response. And then, of course, no system is complete without a cost requirement, so we'll also be integrating in a cost model. And in this case, our requirement is to keep that overall combined cost below $130 million. So now let's talk a little bit about the individual models that we'll employ to determine how the overall system is performing. First and foremost, let's talk about the SysML, the descriptive model that actually tells us what's going on in this system throughout our design and engineering process. So here you can see just a couple of snapshots out of the SysML diagrams. Here we have a basic structure diagram that shows that we have multiple different layers in this constellation. You've got the communications and you've got the sensing constellation. And then, of course, you've got the requirements here. So one of the other models that we're going to be using is something that tells us about the sensor characteristics that we're going to evaluate in the scenario. So as I mentioned before, we're looking at some low-cost Cubesat models for the sensing constellation. So to go along with that theme, what we're looking at here is just a catalog of available sensor payloads that we could use on the system. So we're going to go ahead and just import existing sensor properties from a database, or in this case, an Excel spreadsheet that defines those characteristics that will influence our analysis. When we talk about the antenna design, we're actually employing some very complicated methods from Ansys and their HFSS antenna toolkit. So here, what we've had done is we've had an omnidirectional antenna designed by the engineers at Ansys. They went with a helix antenna, and they specified all the size and shape based on criteria that we had supplied for them. And in the end, they have provided us with that antenna gain pattern. Another model that came from the Ansys team in relation to the communications quality is the overall transient thermal analysis on the spacecraft. So that takes into account not only the environment that it's operating in here, so you can see in the background you have the vehicle environment and the overall temperature of that environment, but then in the lower right-hand corner you can see the thermal analysis of the individual onboard components on that spacecraft resulting in the overall transient thermal analysis that tells us what is the thermal state of any component on that spacecraft at any time. And again, in this case, the reason we're concerned with that thermal state is because any additional temperature at the receiver adds additional noise to that communication link. So we need to understand what those values are when we plug it into the model to evaluate the overall system performance. And then, of course, as I mentioned, it's not complete without a cost model. In this case, we're using a very rudimentary cost model in Excel, but it's going to go ahead and tally up the individual cost for each of the sensors, the communications payloads, and the satellites, and then the collection of all of those together. So now let's talk about the mission model. So we're going to be using STK to bring all of these dynamic models together into one common mission environment, and we can now understand how the overall system of systems will behave. So for those of you that aren't familiar with STK, it's a dynamic physics-based simulation engine that lets us model how things move and how things interact. So this is where we can link the mission to all the other component models across the lifecycle. What you're seeing here is a single imaging satellite with its sensor payload attached. We can already see how that satellite will move over time, which gives us access to hundreds of other related data providers, like the relative position and orientation to targets, lighting conditions, and even the space environment radiation. But, as mentioned before, we're not interested in just a single asset. We want to evaluate the performance of the entire constellation. So here we can see that our constellation design team is settled on 9 sun-sync satellites that are spanning 3 planes that are phased throughout the day, resulting in the desired revisit time. If you're interested in seeing some constellation design activities, go ahead and check out online what we've done with Phoenix Integration and other partners at agi.com/DME. When it comes to modeling the payload, we've got inputs available for the focal length and detector pitch that are going to drive the resolution performance of the overall camera. But this is a good opportunity to point out that STK allows users to model sensors at varying levels of fidelity. So in our current example, the simple geometric calculation will allow us to eliminate many of the infeasible designs without wasting time on heavy computation cycles. But once we reduce the number of options, we could easily increase the fidelity, as you see here, using STK's EOIR module. So that's the imaging payload. And again, that same payload is actually attached to every item in the constellation. So we only have to model it once, and we can reuse it on all of the other objects here. But let's not forget all the other components of the mission that we're working on. So now I'm going to go ahead and add in that communications layer. So you can see here that we've got a constellation of 7 planes and 7 satellites per plane. On each of those satellites, we've attached an antenna that'll be used for both the space-based communications as well as the ground station communication link. So the antenna has been designed as an omnidirectional antenna to support comms in all directions. We'll talk a little bit more later about how we came up with that antenna model, but for now, I'll just say that we're importing that data from a standard antenna gain pattern file that you can see here. The benefit is that as that antenna design changes, it's in the same file format, so we can update the model in our mission simulation, as you can see here. So now that we've assembled the components of our system of systems and we've integrated the digital twins of our various components, now we need to evaluate the overall mission performance. So as a reminder, the system design requires that the sensing satellite has a connection available back to the ground control station at all times through that comms relay constellation, which I'm showing right here. So there's 2 different analysis objects in STK that we'll use to evaluate the measures of mission effectiveness. One is a chain object that I'm showing right now. It connects the initial sensor through the collecting satellite transmitter to the communications relay receiver, and finally from the relay to the ground control station. So as you can see, at some times we have multiple link options available, but at other times, like right now, there is no link available at all until that link is available again. So the second analysis object that I'm going to describe is what we refer to as a coverage definition, which allows me to evaluate coverage across a region or to a collection of locations. So you can see here now that I've imported the GIS shapefile from the website that I mentioned earlier. So each of these points on the ground represents the location of one of those wildfires. So I'm going to go ahead and back up the timeline here. So let me launch my timeline view, and I'll scrub the timeline back to a point before I make this pass. In the 3D window, you should be able to see that the ground targets are getting illuminated when the sensor crosses over. However, as soon as those chain link lines disappear, what you'll notice is that the ground targets in the sensor field of view will no longer be illuminated. So right about now, we should start to lose that connectivity. And there you see the ground targets are no longer illuminated, meaning that I'm not actually collecting imagery at this time because I don't have that constant link back to the ground control station. So from the many thousands of different data providers that I've got available in the scenario, I've selected just 2 to poke at the questions that we mentioned earlier. So looking at the ground sample distance of all the imaging opportunities to ensure that I can detect the wildfires, and then also the revisit time at each one of those points to make sure that my reaction time is adequate to deal with those events. But again, I just want you to keep in mind that behind those 2 simple numbers, the ground sample distance and the revisit time, are a complex web of relationships that encapsulate all the other information produced by all the other tools in that digital engineering ecosystem. So now that we've talked about all the different models that represent the components and the subsystems in our overall system of systems and the mission, let's talk about how we're actually performing the integration to move information from one model to another. So in today's demonstration, we're going to be using Phoenix Integration's ModelCenter to orchestrate this entire integration process. So there's a couple of different tools that we'll be using from ModelCenter. One of them is the Integrate tool, which allows us to connect all the different tools. So in this case, connecting Ansys and STK and Excel and any custom scripting tasks that we're doing. Then we have ModelCenter Explore, which allows us to execute trade studies and investigate the trade space based on the input parameters available to each one of those models. And then finally, we'll be looking at ModelCenter MBSE, which allows us to connect these executable models back to the descriptive models in SysML, and then we can orchestrate the rest of this process from whichever tool makes sense to us, either from within your Cameo SysML environment or to reach back and grab the SysML values from within the ModelCenter environment. So in general, you see the image here shows that ModelCenter ends up really being the conductor to help all the other tools know when it's their time to execute and where the data should go. So to do that, what ModelCenter really does is it provides plug-in points for any individual tool to have a very generic wrapper wrapped around it. So once you put that wrapper around it and integrate it into the ModelCenter environment, you effectively just have a black box for each one of those items in the workflow that takes a series of input values and returns a series of output values. Fortunately for us, ModelCenter has already come packaged up with a variety of industry standard tools that are already wrapped for us. So when it comes time to integrate tools like STK, Ansys, and Excel, these are already pre-built wrappers that make this a very simple drag and drop kind of exercise rather than having to write a lot of custom code to access each one of those tools and to get to the underlying data. So now let me go ahead and just show a quick demonstration of actually executing the workflow that we've established here. So what you can see on this page here is I've got a variety of different inputs. So in this case, I'm choosing a very specific sensor option out of that catalog that I described earlier. From there, I go ahead and run the scenario. You can see it's stepping through each one of these boxes. So it's grabbed a representative configuration from my catalog. It's performing the thermo calculations on the antenna. It's looking at the resulting gain pattern and is converting that into an STK format. And then finally, it passes all of that information into our STK scenario, where we then compute that revisit time, the ground sample distance, and the overall communications quality and the system outage there, as well as computing the total system cost. So now that we've actually orchestrated all the different tools together, and we can execute them in the appropriate sequence, and we can get all of the models passed between the different tools, let's talk a little bit about how we connect that back to the SysML process and to the authoritative source of truth. So again, this is going to use that MBSE package from ModelCenter. So the idea there is we've already constructed our ModelCenter workflow that takes into account all those different subsystem models that we described earlier. We've also have the SysML model of the system, so that descriptive architecture. So the thing that MBSE is going to do for us is actually make a two-way communication path that allows ModelCenter to extract information out of the SysML, and then as well as pushing information back to the SysML. So once we've settled on the appropriate design for the system, we can save the characteristics out of our ModelCenter workflow back to SysML so that the authoritative source of truth is updated and everybody else will now understand what analysis and what decisions have been made. So now let's go ahead and walk through the process of actually integrating the SysML with the ModelCenter workflow. So what you're seeing here is an example of actually opening up that MBSE tool inside Cameo. So first and foremost, at the top, you'll see a server address. So what's going on here is all of the different models that are available across my organization are being served out through the analysis server by ModelCenter as well. And so what we can do is we can link up to any one of these individual models, and we can see on the left-hand side, I'm linking up each of the individual parameters in my SysML diagram to the corresponding parameters in the ModelCenter workflow. In addition to just linking the parameters to evaluate any individual parametric analysis, the other thing that we need to specify is how those parametric analyses link up to the requirements. So what you see going on the screen right now is actually defining what requirements are in my model and how those are connected to individual parametric analysis diagrams. And then from here, we're also specifying the different bounds on those requirements. So in this case, we're looking at one of those metrics coming out of STK, the revisit time. So we're specifying that as a real value, and then now we need to specify what the bounds on that value are going to be. So once we've specified all those different characteristics, we've actually set up an execution plan. So now we know how the different parameters in our ModelCenter workflow link up to the SysML diagram. We now understand how those analyses are driving and connected to the requirements that are specified. So now we can go ahead and execute that overall analysis, and down at the bottom, you can see the results that are coming back to us and whether or not they meet the overall requirements specified in SysML. So in this case, I have actually satisfied all of the requirements of my system, and I can even see within the margin column by how much I've beat those individual requirements. And then of course, here we're saving those values back to the authoritative source of truth. So now we've shown not only how you design each of those individual subsystems, how you link those into the overall mission evaluation, and then connecting that mission to your SysML process, your Cameo tools, things of that sort. But of course, as we're talking about the overall life cycle of things, things are going to change. So when you move from that concept design phase into the no-kidding engineering phase, there are going to be a lot of those models changing. So specifically what I want to talk about is what happens when you increase the fidelity of an individual model. So here's a perfect example where the initial antenna gain pattern that we received for the communications asset was a very idealized omnidirectional antenna. Now, it was based on some very complex algorithms in Ansys, but that was only the size and shape of the antenna. But later on, as the program has matured, we now have a fully featured CAD model for the spacecraft, and we've specified where that antenna is going to mount. So now we can go back to the original Ansys model. We can add in, as you're seeing here on the slide, the CAD geometry around the transmitter or around the antenna. And because that's all wrapped up in that one ModelCenter block, it makes absolutely no difference to any of the other blocks downstream. So when the Ansys model updates, as we run through this block, you're going to see the different results. So over here on the right-hand side of the screen, you're seeing the before and after shot of what did that antenna gain pattern look like before we considered the as-installed performance and the reflections off of the CAD model that we've employed here. So again, to us on the execution side, it's transparent. When the model updates, that block is fully encapsulated and the new information is passed downstream. So in the end, we now have the ability to directly integrate that higher fidelity antenna gain pattern into the exact same STK mission environment that the previous low fidelity antenna was evaluated in, and absolutely nothing changed in the orchestration of the overall model. So again, just to point out that as these models grow in fidelity, the system is already set up to handle that, and it should be seamless for all the users. So, just like a fidelity change to the model, sometimes you're going to have that change come from the outside where now the requirements are going to change. You've got all of the same models, you've got all of the same characteristics to the system, but now we've changed the requirements. So to illustrate that, let's go ahead and actually change the requirements of the demonstration system today. Previously, we had talked about detecting a 2-acre sized wildfire. Well, let's just say that some new research has come out and it suggests that there's an inflection point between 1 acre and 2 acre, and we could significantly reduce damage if we're able to catch those fires when they're much smaller. So now, instead of a ground sample distance of 10 meters, we now need to refactor our system to achieve a ground sample distance of 6 meters or less. You'll notice the rest of our requirements have stayed the same. So to evaluate this, really all I need to do is go back and reevaluate the overall model. So let me show you an example of doing that. So here, again, through the SysML interface here, what I've done is I've linked back to one of those execution plans. And now I'm looking at the individual parameters coming out of that execution plan. So here, the only thing I'm varying is the sensor option that's available to me. I'm keeping everything else exactly the same as it was before, but I'm looking at the response coming out in all of the other system requirements again. So I've gone through, I've ran that trade study, and I have all of the new sensor options printed out here, and it tells me the overall results for the overall system based on which sensor I'm choosing. So in addition to just looking at this from a data table standpoint, we can scroll through here and we can figure out which of these individual options meet the requirements. But we also have the ability to look at these in a little bit more detail, or to look at the data set in a variety of different ways. So instead of just scrolling through and looking at the different options, in this case we've only got about 8 or 10 options, so we can easily find 2 other options here that satisfy our requirements. But let's go ahead and create a new data view that'll actually be a 2D scatter plot. So now instead of looking at a data table, we can look at a graph. And from here, it's pretty easy to see where our requirement line is right there at that 6 meter ground sample distance. And so now here we can see those individual test points that satisfy our requirements. So again, the benefit here is when those requirements change on you, all you need to do is go back to the trade study tools and reevaluate any of your open options to then see which of those new characteristics will meet the new requirements. So let's go ahead and review all that we've talked about today. What I've got on the screen here is, again, that ModelCenter workflow that we've designed that connects all of the different tools in our system of systems. So to remind you, we looked at the individual components for the various parts of the system. So from a catalog, we're selecting a sensor. From the Ansys tools, we're evaluating the antenna characteristics and how the environment has an impact on the antenna performance. And then, of course, we took all of those models and we integrated them into the mission environment. And then once we ran through all of those, we were able to get the results back out to tell us, based on the inputs we selected, are we meeting the objectives on the outside? And then, of course, from there, we went through and we connected that back to the MBSE process by linking these executable models to the SysML diagrams and requirements. So in the end, AGI's overall vision is a fully connected digital thread with a common mission environment at the core. So executing those model-based system-to-systems interactions in that consistent physics-based environment really creates that true mission digital twin. And of course, as those models evolve throughout the life cycle, they can be reevaluated in that common mission environment, along with all the other systems, and you can really assess those objectives. So through digital mission engineering, we're now capable of evaluating the overall mission impact of even the smallest change to any one of those components.